everybody. Thanks for having me. My name is Ritchie Vink. I'm the author of Polars and since a few months also the founder of a company with the very original name Polars Incorporated. I have a background in machine learning and software development, and as I said, I'm the author of Polars and started a company. And today I'm going to talk a bit about Polars. First, a short introduction, what Polars is. Then we're going to talk about expressions, which are one of the most important things in Polars. And then we're going to talk about optimizations and parallelism. Both are very fundamental in Polars, and we guarantee a lot about it. And I want to show you, we're going to end off with a new thing, sort of a demo on Polars plugins, which is something really new and we're really happy about, so we want to share this. Can I get a quick raise of hands of people who already know about Polars? Nice. And using it? Is that the same? Check. Okay. And the rest? Who knows pandas? No, that should be higher, right? That's not correct. Okay. So that shows we cannot trust these votes completely. What Polars is? Polars is sort of a synergy between all DataFrame libraries for a single machine. Talk about data table, dplyr, pandas, and databases, Postgres, Snowflake. And actually, what we saw in the world that for a single machine, we saw that DataFrames were actually reasonably naive, and DataFrames did all the smart, databases did all the smart stuff. They come with optimizers. They can handle data sets that are way larger than your RAM capacity, and they also seem to be super fast. So, it didn't make sense that we didn't have all these nice things in a DataFrame library. And what I wanted with Polars is that we empower your laptop. We empower your single machine. We want to go use all these resources we have available. We have disks, so we can use it. We can probably process data. We don't have to fit everything in memory. We have multiple cores. My machine has got 16 cores. Let's use it as much as we can. So that is the goal. And Polars is sort of a synergy between these two worlds. It's the DataFrame library, which respects all the research done in relational database management. A few things which we have and which are important here are, one thing is very important, and that's that we have lazy evaluation. If you don't have lazy evaluation, you cannot do anything because you just have to do what the user says, and an example is sort this data and then give me the head. Then I first have to sort all the data because that's what you requested. But you only wanted the first 10 rows, and actually a top K algorithm would have been way cheaper. But we have to have a lazy API to be able to even recognize this. Polars comes in two APIs. We have an eager API and a lazy API, and they are both similar or very similar. So the eager API is just for ease of use, and if you want to go to more of an ETL pipeline, you transform this into a lazy just by saying, okay, now it's lazy and now we collect at the end. And then Polars will do all the optimizations for you. We minimize materializations. We do this very often in a lot of operations. For instance, as I said, if you do a join or a group by and you only want the first 10 rows, you shouldn't finish this whole operation first. So in that sense, we only materialize what's needed, and this already saves a lot of compute. We have data types which are constructed to amortize access and allocation costs. As a counterexample, the default pandas string is the opposite of this. They're improving, they're going to PyArrow. But we also are Arrow native, but we are very aware on how we construct these data types. For instance, if we return something in parallel, we know how to create a list, and we know how we can do this stuff in parallel. So we are very careful in how to materialize our results. It's written in a low-level language. and this is very important to have full control over performance and over memory, especially memory. You need to be able to reason about memory to be able to get good performance. Otherwise, you will have cache misses everywhere. Cache is one of the most important things if you're talking about local compute. So it's written in Rust, and this gives us, one, full memory control, and two, it gives us a lot of, the second thing is safety, but the third thing is also, it gives us a lot of good threading, a lot of good concurrency primitives, and we can actually be very sure that we don't deadlock or we don't make these very hard mistakes. And it's designed for effective parallelism. And effective parallelism is something that isn't very common in Python. If we talk about job-lib or multiprocessing, that's not effective parallelism. We need to first serialize the data, move it to another process or another thread, and then deserialize again. This has very non-significant costs to be able to do this. In polars, we just share pointers, and maybe we lock a mutex somewhere, but we are very much designed for effective parallelism, and our algorithms are designed to be lock-free most of the time. It's designed for out-of-core processing. We're getting more and more support for this. That means that we can spill to disk, or we can process data that doesn't fit into memory by working in batches, for instance, and just ensuring that the results get smaller. And we have tight integration with I/O. So this is currently only for local files. We have very tight integration with I/O, meaning we directly read into the memory we need, and we don't have any double copies. For cloud support is getting better in polars, but we still have a lot to do. We're relatively naive there yet, but we're getting better. The most important thing in polars is the API and the expressions. And I'm not, this is, I cannot sell them completely in this talk, I think. But what we often hear is that people come for polars for the speed, and they stay because of the composability of our API. If you learn polars expressions, you learn a new domain-specific language, and you can reason about this language, and then you can use this everywhere. Polars accepts expressions in almost all these operations, and expressions are building blocks of functions, functional constructs, which are pure. They take in some state of a data frame or series or a group, and it produces an output series. And what this series can represent depends on the context. It can represent a column or a group or a list element or a single value or literal. But it's very much like a programming language. If you, for instance, take the Python vocabulary, it's pretty small. It fits on a piece of paper, I think. But all those keywords can be constructed and composed to be Turing complete. You can do anything with it. And the expressions are, they're not as rich as Python, of course, but they are very powerful, and you can combine them indefinitely. You can combine expressions the way you want. You can do if-else constructs, and they are accepted everywhere. So if you're able to do an expression, we guarantee that it runs in parallel, we guarantee that it runs fast, and that we can optimize it. So here's an example of a pivot, an example of a rather complicated expression which you can do in a pivot aggregation. This is just a trivial example where expressions are first-class citizens and are accepted in almost anywhere in our API. So they're accepted in select or with columns, in group by, in aggregations, in pivots, in join keys. In the future, we're also going to add non-equi joins, where you can say, okay, I want to join where this condition is true, and then you can define your own condition. And we are so serious about using expressions that the worst thing you can do is using a custom function and apply a lambda where we had an expression for this on the table. So if you use your own custom functions, for instance, here you use JSON.loads, which would require us to materialize this string to Python first, do a heap allocation, do the JSON.loads, get a Python string back, and read that and push that back into our own memory format, which this would be really slow. For 1, the heap allocation, 2, Python, 3, because we need to lock the GIL, so it also blocks all parallelism we can do. So what we do, we actually read the bytecode of your past function, and if we can see that we could replace this with an expression, we give you a warning where we give you an example of how you can replace this expression. And we can do pretty cool stuff like arithmetic, NumPy functions. So yeah, I'm pretty fond of this. I just think it's cool. So there's a promise we make with our API, and that is if you use our API idiomatically, you will get C speed. That's what you get because it's compiled in Rust, factorization. But you get more than this than when you use NumPy. When you use NumPy, you only get C speed. When you use Polars, you also get optimizations because Polars is lazy, and we are able to prove that we can remove some operations that are unnecessary or can be done otherwise. Second thing you get is parallelism, which you also don't get in NumPy. NumPy is eager, needs to execute it immediately, and probably might need the previous result. It cannot know how to parallelize it because it's not lazy. So in Polars, you get parallelism and effective parallelism. And thirdly, you get out-of-core processing, which is, this depends on the operation. Not all operations are supported out of core yet, but we're getting more and more operations in out of core. So the first thing, as I said, is optimization. And different from NumPy, you not only get C performance, but you also get optimizations. Here's an example of a query where we scan a Parquet file. A scan in Polars means we read the file, but we build a graph, a DAG of operations we're going to do. So if you read, then it's eager. We will read immediately. If you scan, we will build the node of the DAG with the promise we're going to execute this when you're ready building your DAG. So that's what the scan does. Then we apply a filter, we do a group by, and then we do a mean and a sum aggregation of some multiplication of 2 columns. And as you can see, this multiplication is done twice, right? So what Polars, I'm going to show this later, but what Polars already recognizes is that this multiplication is done twice and we only need it once, so we can cache it temporarily. But if we run this query without optimization, it runs in 1.07 seconds. And if you run this with query optimization, you get a 4.5 times speed up for free, doing nothing. You can just write your query semantically as it should be read. So what the goal of Polars is that you can focus on your business logic and you can write your queries in a readable fashion. And we don't want to get unreadable queries because this should be faster, because we should be able to do these optimizations for you. So here's one optimization. As I already said, this multiplication is double. So what we do, this is called common sub-expression elimination. When we see common sub-expressions, we will cache them temporarily, so it will only be executed once. And as you build more complicated expressions, it gets more and more common to get common sub-expressions. Or if you have an if-else branch and you want to get the result of the predicate also somewhere in the else branch, you probably also often have common expressions. Here is a non-complete list of the optimizations we do. One thing we do is checking the schema. Polars is strict. We need to know the schema of the data types up front. And I think this is super important. You don't want to be in a query 20 minutes in and get an error. Oh, expected floats, cannot use this in a hash map. This should be known up front. And in Polars, the data type always depends on the operations and never on the data. The data should not change a column into a float or an integer. Missing data and none should not change this. So that's the first thing we do. Another thing we do is the trivial stuff, projection pushdown, predicate pushdown, which means we look at which columns you need and only load the columns you use. And the same for predicates. Predicates is a fancy name for filters. We apply them as early as possible during the reading. Parquet files have statistics, and sometimes we can even prove that we don't even need to load this Parquet file or this part of a Parquet file based on those statistics. Or even better, sometimes we can prove that we don't even need to download this part of a file based on the statistics. We do some join branch reordering, not super fancy yet. We're gonna improve this later. We don't do join orders, but we swap the branches if we can prove that one branch would be faster than the other. We do scan sharing, meaning that if a part of a query or part of a scan is used multiple times, we cache it in between, so you don't load the same file twice. Common subplan elimination and common subexpression elimination. We saw the one just yet, and type coercion. The second thing you get if you use polars idiomatically is parallelism. And we use a technique for that called work stealing. And work stealing is super effective. I'm gonna explain it a little bit. It works with, one, it's very cheap. We don't have any serializations. We don't have any thread or startup costs because we start our threads up front. When you start polars, we allocate a thread pool, and these threads will be used for the compute heavy stuff. By default, it's equal to the number of cores on your machine. So for my machine, we'll start with 16 threads. And those threads will be reused. And starting a thread can cost 100 milliseconds or so. So it's non-trivial startup cost. Every thread has a queue dedicated to that thread, and we can publish work on these tasks, on these queues. And then this thread pool thread will just keep finishing its task, right? But when a thread is finished, and it has nothing to do anymore, it will steal some work from a queue from another thread. So here we see this thread is finished. It has taken half of the work of the other thread. And Polars uses this throughout the library, throughout the framework. And we are actually very able to keep all your cores saturated with useful work. It's important for us that we create tasks that are somewhat equal. As you can imagine, if you have one task that takes half an hour and the other, that's extreme time, but one task that takes super long and the other tasks are already finished, you cannot share it. So the task should be evenly sized, but this is something Polars tries to do for you. You don't have to think about this. And because we allocate less or equal to the number of cores on your machine, the OS doesn't need to swap between threads. And swapping between threads is very expensive. If you have 1,000 threads and you only have 8 cores and you give all those threads useful work, you will have a lot of overhead of swapping threads, clearing the state of that thread. Will be a lot of system calls. Here's an example of how we deal with the parallelism, where Polars has different strategies depending on the group, on the context you run. So here we create a DataFrame with, I think 10 million rows and 1 million groups. And first we count the number of unique elements and we multiply it times 10 in a select context. And what we do then is for the n unique, we create different tasks. We parallelize this over all the queues. But for the multiply times 2, we don't, because a multiply is often very cheap. The threading overhead wouldn't be worth it, especially if you talk about SIMD acceleration in arithmetic. So the n unique we determine to parallelize, and the times 2 we don't. In a group by, we create groups, right? The group by. And in this case, we have 1 million groups. What we do is then we only parallelize over the groups, and we don't add extra parallelism between the NUnique call, because it's not needed to also split the NUnique again. Otherwise, you would have a parallel task with the group, and then the NUnique would also chart out in more tasks. Here we don't do that. And again, the ×2, we ignore the groups because it's cheaper to just do it. This is an example of how Polars chooses to split up its tasks. We may change this. There's no guarantees here. We try to do this in a smart way under the hood. And yeah, as I said, we have a thread pool, and this thread pool is concurrency aware. So it's not bound to one query. You can actually put polars behind the work scheduler like Airflow or web server and push work on polars, and you will not get saturation of your threads, because the jobs, the task will just be added to the queue, and it will continue its work, but you will not get any saturation or any it would not limit. The third thing you get, I think it's a bit more obvious, is that you get performance with the expressions, right? If you don't go into lambdas, into custom Python code, you get C-like performance because it's written in Rust. And we control every performance critical code branch. So we've gone through a lot of effort to use very, very fast algorithms, which are cache efficient, use SMD vectorization. We try very hard to reuse memory buffers because heap allocations are very expensive, and we parallelize effectively. But because of the expressions are super composable, it's actually the amount of lambdas you need, the amount of custom functions, UDFs you need, are way less than in a tool like Pandas, for instance. And as a result, we are very fast on local data. We're one of the fastest in-memory query engines if the data fits in memory. These are the results of the TPCH benchmark. I heard from Matt that Dask will perform better with the new version. So there will be a new update on this. Tomorrow there's a talk on TPCH benchmarks, which scales to terabytes in the cloud. That's something Polars isn't really. Polars is mostly for local data. If you have local low latency data, Polars will. So compute-bound data, Polars is a very good choice. And as you can see, it's super fast. So the fourth thing I want to show, I've been talking a bit about expressions, and if you use the expressions, you get a lot of benefits, right? But we cannot solve every problem for you, every expression you can think of, and we also don't want it, because then our library would have a feature explosion, and you would need to download 200 megabytes or 400 megabytes to get Polars installed. So there needs to be a way for you as a user to benefit from this, to get expressions with your business logic that can hook into our engine. And that's what Polars plugins is. So you are able to compile your own Rust expressions, and they can link into the default Polars engine. So you pip install Polars, you compile your own expressions, you can also publish them on PyPy, you install that, and then we symbolically link your custom expressions into our engine. You can register them and you can run them. And you will get all the stuff from above. You will get the parallelism. We don't have to go through Python, so there will be no GIL interference. You get optimizations. We can use some of the characteristics of the functions. So as CSE, the common sub-expression elimination, we can use that. The first-class citizens, so everywhere where we accept an expression, we also accept your expression. And as an example, I want to make a Pig Latin converter. Is anybody familiar with Pig Latin? It's a silly language where you take the first letter, put it at the end, and then you add I, sort of piratey. So pig Latin would become ik, pi, add in lay, lie. I don't know how you pronounce it. Lay. And we're going to do this okay, now let's do it on a few different ways. Let's do it first naively with a Python lambda, right? That would be worst. And let's see what's to win there. So here we have a data frame with 5 million elements and 16 columns, which would be 80 million strings. Strings are expensive data types. So the naive way would be a Python function, piglatinify. I think it's correct. Correct me if it's not. And then in polars we can, so the comments are called comments 0, comments 1. We can select all columns with a regex. So this is so this expression expands to multiple expressions. And then we apply this piglatinify function. And let's take a look at, oh, this doesn't work. Well, let's run this thing. And the parallelism is super bad, as you can see on top, right? So this comes due to GIL locking and heap allocation. The memory is also very bad. I looked at what happens, and it seems that Python just frees everything when we give back the control. So the memory is not really good, but the parallelism is terrible, and now it's finished. And it should have taken approximately 23 seconds, which is terrible. A better idea is to use a polars expression, right? Polars expressions are composable. We can just make an expression. We take the comments, we slice from the first point, and then we take the first character and add I, right? And this should be faster. So, yeah, it's already done. So, and as you can see, it was completely parallel, right? Also way better on memory, but we want to have the fastest big Latin converter in the world, of course, and we want this thing to be super parallel, so we're going to build our own big Latin converter. And we can do that. Who knows a bit of Rust? A little bit. Okay, I'm going to talk you through it. The Rust is rusty. We have Polars is a DataFrame library written in Rust, and you can actually import this DataFrame library and compile it. We actually have a frontend in R, we have a SQL frontend, we have a CLI, we have a Ruby frontend, we have a Node.js frontend. You can take our crate, compile it, put your own language bindings on top of it, and you have a DataFrame library or a query engine. So you can take the polars crate, you can take the PyO3 polars, that's the crate that helps us derive our own expression. And Serde does some serialization and deserialization, that's some utility crate we need. And this is a memory allocator, you don't need it, it's boilerplate, you can use it, it makes stuff faster. And the first thing we have is a quars, keyword arguments. And the arguments, if you want to accept arguments in an expression, you can create your own struct and add derive, deserialize on it. And then you can add anything you want, a Boolean, an integer, a list, and this will work automatically. We will ensure this will get deserialized. Here we have the function that does the conversion, and then we register the expression itself. And the expression itself is a function that takes as inputs a Rust series and the keyword arguments, and then we add a derive boilerplate thing where we say, okay, this is a polars expression, this is the output function. The output type can be fixed. You can also provide a function that determines the output type depending on the input type. And then we apply this, this conversion, and that's it. Then we can compile this. And on the Python side, we create a package with the name of our package, and we add an init. And there's a little bit of boilerplate. We need the lib is get shared location. You can create a language or any class, utility class, and then you can add your own functions. And you see the register name expression. There you define under which namespace this expression will be available. So here we're going to use the pig namespace. And then we register the plugin. And that's it. So now we can compile this thing. Voila. Normally it takes a bit longer. Compiling polars isn't, it takes 5 minutes or so. Take a cup of coffee. I pre-compiled this one. And then what we can do is just import pig Latin, that's all. And now it's registered, and now we can use the pig Latinify expression. And now we have the fastest, not the fastest, I don't know. We have a very fast parallel pig Latinify converter. Also, as you can see, runs in parallel. We cannot even get up to speed because it's done so quickly. So this took 368. It's 2.5 something compared to normal polars expressions, and compared to the naive solution, yeah, it's not really fair, right? That was 25 seconds, 23. So yeah, that's the plugins. I want you to take home that the polars expressions allow you to do a lot of stuff and will be super vectorized, will be super parallel, and are super composable. And if you still need to do your own stuff, you can do this with the polars plugins, and you will have the best of both worlds. And as last thing I want to show is a bit of how polars is sort of hybridly out of core. So we can process data sets that don't fit into memory, and if we cannot, we don't support our whole API in streaming, but we support parts of it, and we can do this hybridly. So if the first part of your query fits in streaming, then after that we switch to the default engine and you can continue. And this allows you to process data sets that don't fit into memory, because there are a lot of stuff that reduce data. For instance, a group by reduces the data to the cardinality, right? To the cardinality of the groups. Limits, predicates, all this stuff reduces data. This query actually runs completely in memory. But here we scan a Bouquet file. I'm gonna collect it to show you the size of this file. It's quite big. It takes half of my RAM, I think. So let's do something. Let's start this again. And now we're gonna build a query, and we're gonna concatenate this large table 4 times, so it definitely doesn't fit into RAM. And then we're gonna do this query, the first query of TPCH. And we're gonna run it in streaming mode, which means, okay, try to use our streaming engine if you can. And I just want to show that we are able to do things super parallel, and we can really work without a lot of memory pressure. That's the takeaway I want to give here. And now we're done. I just want to show if you write your queries idiomatically, we should be able to do things smartly, and you should not be worried with batching and that kind of stuff. And that were the takeaways I want to share. This is my final slide. We are super active on GitHub, and 2 on Discord. There's a lot of people helping out. So if you got questions, go to Discord, say hi. Say hi. And thank you. Yes?
So what was the difference between the plugin? What happened that you found to speed up by making our own plugins?
versus the expressions.
Expressions of
Right. Well, let me go to, and expressions are, where is the expression? Here's the expression. Expressions run vectorized. So what will happen, in the plugin, I created the function and passed it to LLM or LLVM, which is a higher performant optimizer, which will do all kinds of stuff to optimize this function to work effectively, right? And it doesn't have to do a heap allocation because we also know how to write it to a buffer. In this case, Polars is precompiled and the expressions are generic and they work vectorized, and we can run stuff you give us, but we have to run them vectorized. So here we run first a slice. We will create the first slice, which we'll do a heap allocation of the, and then we do another slice, and then we add this. So you do 3 operations vectorized, but these operations, the compiler, so the Polars has a optimizer which can shuffle operations, can change operations, but we don't have a piglet identifier in our engine. So it will have to do this in a vectorized way, which cannot be as optimized as writing this function in Rust and doing things smartly, right? So it can even be that there is some SIMD optimization in the function that the LLVM optimizer found. But yeah.
I really like the import pig Latin part, the fact that it ties into Python. Can you talk about the magic for like how you get the compiled Rust to be like importable?
The magic, how we get, so on the Rust side or on the Python side?
It's, how did so we compiled that pig Latin extension, and then you were able to import it, as if it was like a site package.
Yeah. So there was some boilerplate in the. Here's a boilerplate get shared lib location, and the compiled function gets stored in the. You can see it here. It gets stored in the package. Also, if you build a wheel package, it gets the compiled code is next to the package, so it's in the same location. So we ask you to get the shared library location, and then you need to register it here. And then at runtime, we will link. So the Polars engine will take this information, it will link the thing, and then it will call the function when it's needed. But on the moment we call this function, we don't need any Python, right? We know this is the binary, this is the location in the binary file. You only pay for a virtual function call, which in the sense of Python is very cheap. Yeah, other question?
My team uses numba plus numpy to kind of accomplish the same thing that this plugin is accomplishing. We were considering switching to Polars, but I don't think I could convince any of my colleagues to start writing Rust plugins.
Right.
Is there any chance that this could be lifted into like a Python ecosystem, like this plugin feature? So you just write it in pure Python and somehow it calls LVM just like Numba does.
Wow. That's a whole other project for me. No, I don't have any. I mean, you're asking for a Rust, or what we need would be a...
like a siphon for Rust.
Yeah. Yeah.
You need new coworkers.
Yeah. But the thing is, what I want to... So I hope... Rust isn't... It's got a steep learning curve. True. But if you write easy Rust with cloning, you're already way faster than doing this UDF stuff. And if you look at, if you do arithmetic or call a distance function, that part of Rust isn't that hard. I think the lifetimes is hard, the traits, but I think the kind of stuff you want to write as a plugin, the basic stuff, the initial stuff, we already have a business day plugin, which gets in an integer, which represents some epoch time, the Unix epoch, and they do some arithmetic with the chrono library, and you can hack that array. I trust you, you can. So I understand what you say, but I don't think it's the bar is super high. You can already get a lot of added value by doing it in the naive way. Yeah.
So regarding the scan parquet, do you use like PyArrow internally, or
No.
do you use a Rust to?
No, we have our own parquet reader. We built first initially on Arrow 2. Now we forked Arrow 2 and Polars. I implemented the CSV parser. We use SIMD for JSON, but everything is in Polars. So we have a Rust grade, and everything must be compiled with us because we don't want to be dependent on Python, because we also have an R package. We have a SQL CLI. We want to be sort of a bootstrapper of query engine or data frames. If you start a new language and need a data frame, please come to us. We solved a lot of problems already. And you don't have to adhere to our API. You can build your own API on top. That's actually what happens in Elixir. Elixir's got a data frame library called Explorer, which has built upon Polars and actually just uses Polars every month when we make a new release, they update their Polars engine.
But you mentioned in your group by example that group by is parallelized. Do you determine the groups before you do that, or are you caching the groups, or?
Depends on the engine. We have two engines, the streaming engine and the default engine. The default engine computes the groups before, does this log-free with radix partitioning. We have yet another, if we sample first the cardinality in the default engine, and if the cardinality is low, we go to another engine as well. Group bys have very different results depending on the cardinalities, and you need not just one algorithm, because then you will be slow on the streaming engine. The group by is streaming. We compute the groups as they come, and we keep a hot table of hot groups in memory. And if the table grows and we have a high cardinality, we start to spill out to partitionings. And if these partitions tend to go out of memory, then we spill those partitions to disk. And so we do this partially hot tables in memory, and then we have less hot or cold tables for the colder groups. But there the groups are determined while we get the data. Yeah. Does that answer the question?
Yeah. Another question, out of memory, are you using basically like a disk cache?
Yeah. So the worst thing you can do is let the OS swap.
Yeah.
And that happens sometimes. If you have Polar's default engine, we can swap, and sometimes people say, hey, this is slow, but okay, at this point you're not benchmarking anything, because swapping is the worst thing that can happen. But we have a lot of information. We know what's happening. We know which data we need, we know which data we don't need. So what we spill to partitions, depending on the algorithm, these partitions mean something. Sometimes we don't need partitions, we can just spill to disk. It depends on the operation, how we spill. Yeah. Yeah.
You're crazy, man. Congratulations.
Thank you. Oh, cool. Yeah, thanks. Well, I hope you get happy users. We move really fast. If you have an issue, open issue, and it probably is solved within a week and released as well. We really like this fast pace because we get a lot of information out, a lot of feedback. And this way you can also steer where we're going. Yeah. Cool, thank you.